My name is Amrit Venkatesh. I'm a research faculty at the National High Magnetic Field Laboratory at Florida State University in Tallahassee, Florida, in the US. My research involves improving the sensitivity of solid-state NMR spectroscopy. So what does this mean? When you try to obtain solid-state NMR spectra of materials, it takes a really long time to perform complex experiments because of very low signal-to-noise ratios. This means that most of the time when NMR spectroscopists try to obtain spectra of any samples, they're just looking at noise. And therefore, it's important to develop techniques that improve the sensitivity of solid-state NMR. So I work on two of these techniques. One technique utilizes a method called as dynamic nuclear polarization. In this method, what we do is we dope an external polarizing agent into our sample, and this polarizing agent contains electrons. And when microwaves are shined on the sample, we can transfer the polarization from electrons to nuclei present in the sample, which allows the overall sensitivity of NMR to be improved. The other method that I work on is known as indirect detection. With indirect detection, we can use other spine nuclei to look at the nuclei that we are interested in. For example, let us say I was interested in looking at platinum atoms in a material. Now, platinum itself is a very challenging isotope to observe directly. But if I try to perform platinum 195 NMR with indirect detection, I can use, for instance, the nearby hydrogen atoms, which are much more sensitive to detect using NMR spectroscopy. And so in the future, I hope to utilize a combination of indirect detection and dynamic nuclear polarization, which will allow us to dramatically improve the overall sensitivity and resolution that solid-state NMR spectroscopy can provide. So why do we need methods like dynamic nuclear polarization? This is because if we wanted to look at challenging samples, for example, cementitious materials, it is really challenging to apply NMR spectroscopy to understand the intricate atomic structure that is present in these materials. So nowadays, there are a number of research groups that are interested in making cements more sustainable and reducing the overall carbon dioxide emissions associated with cement production. In this type of research, it's important to have methods that can look at the fundamental differences between different types of cementitious materials. Recently, we used dynamic nuclear polarization in the EMSLI group to perform silicon-silicon experiments, which allowed us to look at the connectivity of silicon atoms in cementitious materials, particularly zinc-doped calcium silicate hydrate, at natural abundance, meaning we did not have to subject our sample to any artificial isotopic labeling methods. And what this allows us to look at is the fundamental atomic structure and probe what happens to the cement as more and more zinc is doped into these materials. And finally, what we found is that using dynamic nuclear polarization, we can understand that the chain lengths in the calcium silicate hydrate actually become longer when zinc atoms are doped into these materials, which contributes to the overall strength of the cementitious materials at an early age. So this type of study, which ultimately is very relevant to society, is enabled by advanced methods such as dynamic nuclear polarization. Recently, in collaboration with the EMSLI group, where I was a postdoc, I have been developing biradical polarizing agents for dynamic nuclear polarization NMR. Why is this important? At the heart of DNP are radical polarizing agents because they are the source of electron polarization. Although in the last decade and a half, the field has understood a variety of parameters to control the efficiency of these biradical polarizing agents, we don't fully understand yet how to improve the overall efficiency of DNP. So in my recent work, I have been studying a variety of biradical polarizing agents, and recently we published a paper where we showed that it is extremely important for the electron spin to have strong hyperfine couplings and also to have strong proton-proton dipolar couplings in the biradical molecule. What does this do? This allows the hyperpolarization from the electron spins to rapidly get out of the biradical molecule and to polarize the bulk solution that we have. Today, we are at a crossroads where there are several key challenges that are facing humanity. For example, challenges in health, climate, and energy that need to be addressed at the earliest possible, and we need to develop sustainable solutions for many of these critical problems. Many of these solutions involve the development of new materials, new technologies that in a sustainable way that will ultimately allow humanity to overcome these challenges. The development of new materials is very strongly aided by spectroscopic techniques such as NMR spectroscopy. Therefore, it is very important that we develop NMR spectroscopy into a robust, sensitive technique that can provide rich information in a short amount of time. My research involves making NMR better by helping us perform more advanced experiments in a short amount of time. And these types of research will ultimately allow us to develop new materials in a rational way.